the interface. Now, one of the good things is that if by chance you click on something and you just change the shape like that, you just click Control Z. It really makes AMOS very user friendly. It's one of the best software packages I've ever worked with. Okay. Now we already have one error term or disturbance that has not been named. So I'm going to go back to plugins to label that variable and call. So I click on name on observed variable, and we'll get one automatically. You get a label automatically for it. All right. So far, I think I have what I have done is to create the external representation of the structural equation model. This is a structural equation model or path model because we have a path from one latent variable to another latent variable. What I'm going to do here is to change this back to a confirmatory factor analysis because that's the focus of this presentation. So I'm going to click delete this and delete this. Go back here and click on the draw covariances and draw covariance to again get back the two measurement variables and their covariance relationship. Nice. So I think I'm good to start the parameter estimation and understanding whether this model fits into the analysis, fits into the data. I click on this icon here, which is analysis projects. I go to the first tab. What I would like to do here is, I think this is, I just move it here. What I would like to do here is to choose the right parameter estimation. We've got maximum likelihood and GLS, or generalized least squares analysis. These two are suitable for normally distributed data. I usually go with maximum likelihood analysis. If you have strong evidence that your data is deviating from normal distribution, you should use unweighted least square, scale-free least square, and asymptotically distribution-free kind of parameter estimation. So these three are suitable for nonlinear analysis, but this non-normal data, and these two are suitable for normal data analysis. So I assume that my data is normally distributed. So I click on maximum likelihood. The rest should be left as is. I really don't bother to change any of these. Bias and all that. I mean, they are used, but for different sort of analyses that's not within the scope of this video. I might explain them in another video. So output, I always need the maximization history, standardized estimates, squared multiple correlations, and then direct indirect total effects. This is particularly useful when you are doing a path analysis or structural equation modeling, and test for normality. This is good because you want to make sure that your data was normally distributed. If you want to do bootstrapping, go ahead and, for example, you perform some bootstrapping, just you know, to make sure that your data, the model that you generate is rigorous and all that. I'm not going to choose bootstrapping for this analysis, and I think that should be enough. For permutation and random, we can just leave them as is. Just let me click on this to just show you how that looks like. Okay, so I think everything is ready now. So before starting the analysis, what I could do is to save this model, because if I don't save it, or basically I might lose it. I had already done this before, so you know, I had chosen the name model 1, and I'm going to collect model 1 just to replace it, and click save. Yes, it's asking me if you want to replace it. Of course you want to replace it. So this has been saved. I suggest that you save it too, because you might, I don't know, lose power or something, and the model might just you know, disappear, and you would have to start from scratch. So everything is ready now. On this button here that looks like an abacus or something, you can calculate the parameter estimates. So let's click on it, and that's it. Estimation is over. you can get standardized estimates here and unstandardized estimates. If you see, if you toggle between the two, these estimates change. So you got standardized estimates and non-standardized estimates, like that. Okay, let's talk about these standardized estimates and also the fit statistics. There are two things that we need to take into consideration in arguing whether our model is a good fit for the data or not. Like I said, estimates of those parameters that we defined in our analysis and model fit. I'm going to start with estimates here. There are a lot of statistics here that actually might be confusing. What I would like to start with is standardized regression weights. And any time that you don't really understand what's going on and you don't know what is a standardized regression weight, you see when you put the cursor on that word, on the word of the phrase, it gets active. So you click on it and another pop-up window appears which gives you more information. So if you want to learn more about the estimates of standardized regression weights, you can just click on this option and you will be directed to the manual of AMOS, and there will be a lot of useful information. That's another good thing about AMOS. What happened? Okay. So the first estimate, that's the standardized regression weight for the path that runs from listening 1 to section 1 is 0.772. What does this mean? You just click on it and this pop-up window appears to explain everything. When listening 1 goes up by 1 standard deviation, section 1 goes up by 0.772 standard deviations. That's pretty large, I would say. That means that a large proportion of the variance that you observe in section 1 is attributable to listening 1. That's the latent factor. So yes, section 1 is most likely with a high degree of confidence is measuring listening ability or whatever latent construct that you're measuring. Estimates should be significant and at least above 0.3 to make some sense. Above 0.5 to around 0.7 or 8, they're actually ideal. But the more they get closer to 1, the more you might deviate from the concept of discriminant validity, or the evidence for discriminant validity, which I'll explain in another video. Okay, so then for the covariance, that's the relationship between latent variable 1 and latent variable 2. We got a significant covariance with a critical ratio of 8.137. This critical ratio is estimated by dividing the estimate of the variance, covariance between the two by their standard error of measurement, which is statistically significant. This means that there is a significant covariance or correlation between the two variables. Now, if we can standardize the covariance and get correlations, and as you see, the correlation is pretty high. It's so high that it obviously indicates that listening 1 and 2 are not separable because it's almost 1. When this means that around, let me see, I can calculate the amount of variance that is in common between the two. It's 0.9787 raised to the power of 2. About 97% of the variance of these two latent variables is common. So with such a high amount of variance in common, I don't think that you need to separate them. It doesn't make a lot of sense there. Okay, and the rest of the story is about the variance that was observed in other variables. In the variance observed in listening 1, listening 2, all of them are significant. And also the error terms, they're all significant. Then squared multiple correlations for observed items or observed variables. You can click on it and get get the meaning for this. For the squared multiple correlation for section 4, it is interpreted in this way. It is estimated that the predictor of section 4, that is listening to, explains 60%, 60.1% of its variance. This is pretty good and pretty high. In other words, the error variance of section 4 is approximately 39.9% of the variance of section 4 itself. So the amount of variance that is explained by listening to in section 4 is a lot higher than the amount of variance that is not explained and is attributed to error of variance. Therefore, what we conclude is that this section contributes to the measurement, or this item contributes to the measurement of listening. For section 3, we have more or less the same story, except that those percentages are different. Here we have around 80% of the variance explained by the latent factor 2, and so on and so forth. The total effects are similar to the non-standardized effects that were explained above, and standardized total effects. I think the rest of the story is kind of repeated in some ways. Okay, what I'm going to do is to go back to this site again and click on model fit. Model fit is also a very important part of the analysis in SEM and confirmatory factor analysis. In fact, a lot of people start from model fit. If the model doesn't fit the data, then they don't even bother to look at the estimates. So the first thing is a chi-square value. This CMIN stands for chi-square. So chi-square is a test that shows if the model that you are suggesting, that's the two-factor model that was presented before, is a good fit to the data or not. Now, the interesting thing here is to remember that we would like this chi-square value to be non-significant, statistically non-significant, to show that there is no significant deviation between the data set and the model that we have the model that we have hypothesized. Here, the p-values, you can see the p is 0.331. I can click on this. Assuming that the default model is correct, the probability of getting a discrepancy as large as 0.945 is this, 0.331. So this p-value is not significant, so that's good news for us. That's one piece of evidence that indicates that our model is performing well. Now, this is called normed chi-square value. That's chi-square over degrees of freedom, which gives us this statistics. If this is smaller than 3, it would be another indication that your model is fitting the data well, which is the case here. You see, for the default model, the discrepancy divided by its degree of freedom is this. Okay, so what else? Actually, there are many statistics here. One of the things that you could present is the goodness of fit index, this one, which is 0.998, is pretty much close to 1. Now, how to interpret GFI and other kind of fit statistics is a bit tricky. Some scholars and authors like Hare and his colleagues in their influential book argue that it depends on the sample size. But a lot of people assume that anything above 0.9, or if you want to be more strict, anything above 0.95 indicates that your data has a good fit to the model. Or the other way around, the model has a good fit to the data. Well, sometimes these statistics are larger than 1, like this case, where the CFI, this doesn't work here. Well, this CFI is 1. For the default model, we always focus on default model. This is pretty good news. the TLI is even larger than 1. So is 1.001. This is another good piece of news. So we have 3 pieces of evidence, 1, 2, 3 here, and 2 more here, 1, 2, that our data is fitting the model is fitting the data pretty well. Now, if you scroll down, you'll run into this RMSEA, which is the root mean square error of something. I don't exactly remember what that A stands for. It should be anything below 0.8. Some authors claim that it has to be below 0.08 or 0.05. I mean, there's a range depending on which author you cite in your paper. It could be as high as 0.08 or as low as 0.05. That's the threshold beyond which the data would have a less desirable fit. I mean, the model would have a less desirable fit to the data that you have. Luckily for us here, the Ramsey or RMSEA is 0. That's pretty good. Now, there's also a confidence interval here for the index, which has a low and a high threshold. The low, you can click on this and get what the interpretation of it. With approximately 90% confidence, the population RMSEA for the default model is between 0 and 0.181. So, like I said, the smaller this range, the better it is. And I think this range is really small. And the actual Ramsey itself should fall between low and high, which is almost the case because 0 is 0. I mean, you can't get smaller than 0. So we meet that requirement as well. The other thing that we need to take into consideration is the AIC statistics. The AIC statistics are used for model comparisons. When you have 2 nested models, that's when one model is the same as another model, but with one tiny difference, that's called they're nested, then you can compare them. So these statistics here in this table are used only for model comparisons rather than to investigate whether the model fits the data or not. On their own, they don't make a lot of sense. So you have to compare it with another model to see if their index is smaller or larger. Typically, we would be interested in those models which have got AIC, BCC, BIC, and CAIC coefficients, I mean index values, which are smaller. So the smaller they are, the better they are in terms of the fit. I think that's more or less it. So I would assume that the model that we have generated here, based on the statistics that I presented, is a good one. Is actually fitting the analysis, fitting the data that we have used. There is one more thing before I finish this session. I'd like here to present this. It's the multivariate normality. The multivariate normality, which is displayed here, is in this column here, the kurtosis value. This is the multivariate kurtosis. So for section 1, the last one is the multivariate kurtosis. This is the univariate kurtosis. For section 1, univariate kurtosis for section 2, and all the way down. And the multivariate kurtosis is minus 0.193. This indicates, because it's far below 5, some authors like Klein and others like Byrne actually claim or assume that if the multivariate index, which is actually Mardia's coefficient multivariate index, if it's smaller than 5, then that will be evidence for the multivariate normality of your data. Is way smaller than 5, the absolute value of 5. And I think that just provides enough evidence that the data is normally distributed. And as a result, the choice, I'm going back to the data analysis window here, the choice of maximum likelihood estimation method was pretty fine. If this data analysis here gives us a multivariate kurtosis statistic beyond 5, so you might want to try the other method for parameters, any of those 3 methods for parameter estimation in non-normal distributed data. So this brings me to the end of this video. It's been quite long. Thanks for your patience. If you like the video, please give it a like. And I'm gonna provide more examples in the next video, examples on path analysis and structural equation modeling, and the other software packages which was mentioned at the beginning of this video. Thank you and have a good day.